All right. Hello, everybody. Hope everyone is staying safe and warm. I'm going to go ahead and attempt to lecture from home here over sections 1.3, which we started last time. We're just going to finish that up today. And then we'll do sections 3.1 through 3.2. So beginning with where we left off on section 1.3, this was the correlation and regression part of the chapter. And we did an example with correlation, and we were just getting into regression, talking about what the A and B values mean on the calculator when we get those. So let me stop sharing these notes real quick, and I'll go to my notes from last time. We can just look over this real quick. Okay, so here's where we were. The first thing we did was define what correlation was. So it shows the strength and relationship between two variables. We talked about what positive and negative correlation would mean, right? With these two examples, children's height versus shoe size, those both increase at the same time. So that's a positive correlation. Then the second example, coats sold and the temperature. As the temperature goes up, the coats sold goes down and vice versa. So that's an example of negative correlation. And on the next page, you see a picture with no correlation, where the two variables don't really increase or decrease together. And then you see an example of perfect correlation, which looks like a straight line. So we should expect perfect correlation to form a straight line. All right, and then I made the point that correlation does not mean causation. So just because two variables do correlate together, meaning that they increase at the same time, or as one increases, the other decreases, that doesn't mean that one variable causes the other variable to change. And we did this example in class where we looked at the per capita consumption of margarine versus the divorce rate in Maine. And we showed that those two data sets do have a strong correlation on the order of 0.9. But of course, the consumption of margarine does not cause the divorce rate in Maine. So the next thing I wanted to do was another practice one here. Oh, and by the way, you can see at the top of the page here, here's sort of the instructions to do this on the calculator. But you should have a good video on that with the pre-class lessons. But don't forget to turn the diagnostics on. And by the way, when you're in the testing center, you'll have to do that for the calculators in there. So they usually erase the RAM on those calculators. So you'll have to do this second plus 0, press X inverse, and then click on diagnostics on. There's some instructions in the testing center for that as well. Okay, so let's try out the second example here. So the two variables we are comparing are arcade revenue in billions of dollars and the number of computer science PhDs awarded. So again, two variables that should not cause each other, right? But they may correlate. So just as an example to do this, since I can't show my calculator on this computer, I'm just going to go to a website where I can enter in this information. So if you'll bear with me here a moment. I wonder if I can just share the whole screen. And then we can see both the websites and the data. Let's see. Okay. So this is just an online linear regression calculator. All right. So I'll just keep my labels, doesn't matter so much. So I'm just gonna enter in this data. If you were doing this on the calculator, you would go to the stat button and then enter these into the lists L1 and L2. But I'm just gonna enter them in here. Let's see. 4, 3, 5. 809, 867, 948, and 1, 2. Okay, and so I'm just going to calculate here. And there we go. So the first thing it does is create a scatter plot. So it's got the arcade revenue in billions of dollars on the x-axis, and then the the number of computer science PhDs on the y-axis. And each dot here represents a coordinate pair with revenue as x and then PhDs as y. And then it's also got a line on the graph right here. So we talked a little bit about this, but this is the best fit line. And if the variables were perfectly correlating, each of these data points ought to be on this line. But since it's not perfect, some of them are a little bit off here. Now, this best fit line is what I wanted to talk about next. And this is the part of the section where we do linear regression. So all linear regression is coming up with this line that fits the data as closely as possible. So you can see here, the calculator calculates the slope of this line, and then you can get the y-intercept and x-intercept, so you would actually be able to graph it. On your TI-84, when you do linear regression, so you would go to stat, calculate, and then the number 4 option, which is linear regression. You will, not only will you see the R value, that's the correlation coefficient we've already looked at, you will also see an A and a B value. And the A and B value is the slope and the y-intercept respectively. So when you have those two values, you actually get the equation of that best fit line. So you can see here, this is what the equation ought to look like, right? So a linear equation with the slope on x and then a y-intercept right here. Okay, so that's what this will look like. I mean, it'll look a little bit different on your calculator, but the idea is the same. And I just wanted to give you some background on what this actually means now, and then we'll move on to 3.1 and 3.2. Okay, so let me go back here. All right, here we go. So I'm going to do a just an easy example that we can graph here on a paper ourselves, and then I could talk about how that best fit line is found, and then we'll move on. So this isn't any actual data. I'm just kind of making this example up. But here's a variable x, here's a variable y. And I'm just going to have like 1, 2, 3, 4, and then 2, 1, 3, 5. All right, so let's say that's my data set. Now I'm going to graph my scatter plot. So let's see, my first row is 1, 2, so that should be right there. 2, 1, let's see, should be right about here. 3, 3, let's see, 1, 2, 3, right here. And then 4, 5 would be, I think, right there, if I did that right. Okay, and so if we had to guess, a best fit line might look something like, I don't know, like this, right? A line that follows the data closely. But how I guessed this line, let me actually extend it a little bit here, was by looking at the data and seeing if I could get the line as close to all the points as possible. So what I'm really doing is trying to minimize this distance. Right, so if I can find a line that minimizes this sort of y distance between all of these points in the line, I will have a minimize distance. I will have achieved my goal if I can find a line that does this. And so really what that means is I'm trying to solve actually a system of equations. So the line that I want to find is going to look like this, right? Whatever that best fit line is, it'll have this equation. I just don't know what A and B are. But I do know that I want to get A and B such that the line is as close to those data points as possible. In this example, it can't be on, it can't be exactly on the data points, but it can be close. But ideally, what we would want is for this equation, if I have the correct A and B, if I plug in the X values in my data set, I should get the Y values, right? If the line actually touched all of those points, what I would know, if I look at the first row of my data set, I would know A times the X value, which is 1, plus B should equal the Y value, that's 2. And then on the second row, A times the X value, which is 2, plus B should equal the Y value, that's 1, right? So on and so forth. So ideally, if the line touched every single point in my data set, I should have these 4 equations. And I would hope to solve all of these simultaneously. Now you might notice that this is an equation of 2 variables. And let's see, we have 4 equations. So we call this an overdetermined linear system. It's overdetermined because usually if we're solving a linear system, we should have the same number of equations as variables. But unfortunately on this one, we actually have twice as many equations as variables. So if I were to set this up as a matrix equation, what I have right now is, let's see, a matrix with all the coefficients, right? So it would be 1, 1, 1. I'm looking at the coefficients on A and B. And then I've got 2, 1, 3, 1, and 4, 1. That's my matrix of coefficients. And then I'm multiplying that by the variables that I don't know. That's A and B. And that's supposed to equal the right-hand side. Right, so that's the matrix equation. I could take this from the system of linear equations to a matrix equation. We've shown that before. If you follow the multiplication, right, the matrix multiplication on the left, you'll see we get the exact same equation that we had. Also, I know the dimensions look a little bit weird, but notice that the matrix on the left is a 4 by 2 matrix. And then we have a 2 by 1 vector, right? So I can multiply those together because the interior dimensions are the same. And when I do multiply them together, I should get something with the exterior dimensions. So that's 4 and 1. And sure enough, the vector I have on the other side is a 4 by 1 vector. So the dimensions do match up. Presumably, this is a solvable system. But the problem is when something's overdetermined like this, a solution does not always exist. In fact, it's unlikely to exist perfectly for this system. So you can think about this as 4 different lines, and we're trying to find a point where all of those lines intersect at once. So here's a line, here's a line, here's a line, and one more. So ideally, if this system did have a solution, it would be at the intersection point in the middle. But all it takes is for one of these lines, if I erase this, all it takes is for one of these lines to be just a little bit off. I could have one of them right here, and now all of a sudden there's no solution, right? There's no point where every single line intersects. So that's the same situation we have over here in this picture, right? We do have 4 equations, but they're the best fit line is not going to lie on all of those points. There's just no way. So the only thing we can do is try to minimize the distance rather than finding a line that actually lies on those points. Minimizing the distance takes a little bit more math than we can do in this class, but it would involve, perhaps you could use Calculus 1 to do that. But that's what your calculator does. And so we'll let the calculator handle that. But I just wanted you to see kind of what the game plan is to do this and why it does work. And it all boils down to a linear equation, which does come up quite a bit in real life. All right, so that's the end of 1.3. You should be able to find the correlation coefficient and the A and B values to generate your best fit line using the regression, the linear regression on your calculator. And if you need some more help with that, just take a look back at the pre-class lesson video, and they'll show you exactly how to do that on the calculator. And now we're just going to move on to lesson 3.1. Oh, there we go, 3.1. And I believe that's on linear inequalities. Make sure this is still going. Okay, good. Okay, so the first thing I wanted to look at was graphing linear inequalities. Because it might have been a while since you've done this, so I'll just briefly review, just do some examples. Hopefully that will remind you of what we're doing, and then we'll get more into the linear programming part. All that means is we're going to try to maximize or minimize some systems of equations using inequalities. So let's try to graph some of these. The first one I'll start out with is something that looks linear. All right, so this would just be a normal line, except I have the inequality greater than or equal to here. So whenever you graph one of these, just graph it like a normal line. Just, if we were assuming an equal sign instead of a greater than or equal to sign. First thing I would do is take a look at the y-intercept. It's equal to 1. So I can graph 1 point on my graph already, 1 on the y-axis. And then I would take a look at the slope. That's 1/2. So I know that I should go over 2 and up 1 as I move forward. Okay, so there's my line. This would be the graph if I had an equal sign. Since I have a greater than or equal to sign, we need to do some shading. So you could think about what we're trying to graph as all the points that have a y value greater than or equal to the y values on the line, right? So 1/2 x plus 1 will give you y values actually on the line we just graphed, but I want points that have y values bigger than that. So that's all the points above this line. Right, so you would just shade in above the line. We would also count points on the line, right? So My line is a solid line, indicating that I'm counting points on the line as well, because y can be equal to the points on that line, right? Y is greater than or equal to the points on that line. So this would be your finished graph, right? So you have the graph of the line colored in solid to indicate it's a greater than or equal to, and then I'm shading above because I want points with y values bigger than those on the line. All right, so let's do another example. Here's one that you would not be able to put on your calculator, for instance, x less than 3. Yeah, so if you try to put this on the calculator will only accept y equals sort of equations. You can't have just an x, so you might get a problem if you do that. But we know that if this were, think about x equals 3. If this were x equals 3, that is a vertical line. It's the line where every x coordinate is 3, which sort of makes sense. So it would be, if I plot a few points, all of the x coordinates here are 3. So it is this vertical line right here. So that's if x were equal to 3. But in this case, we're trying to graph x less than 3. So I want points where my x coordinate is less than the line that I just drew. So that would be all the points to the left of this line. So I would just shade in over here. One more thing that we see on this problem is that x cannot be equal to 3, right? It's less than 3, but not equal. So my line should not be solid. To indicate that x cannot be equal to anything on this line, I would actually draw this as a dotted line. Right, so x is less than 3, but not equal to 3. All right, so one more example. We can also have a compound inequality. So just making these a little bit more difficult. Let's see, so -3 less than or equal to -2x plus 1. And this guy is less than 5. All right, so this is kind of two inequalities in one. So one of the inequalities is that -3 is less than or equal to -2x plus 1. So we'll kind of graph that by itself. And then the other inequality is that -2x plus 1 is less than 5. And we'll graph that by itself as well. The first thing to do on a problem like this, though, is to go ahead and get this into some sort of recognizable, y equals mx plus b form, right? In this case, we only have x, so we might end up with some vertical lines again. But let's give this a try real quick. Let me move my notes forward here as well. I probably need to do this on the next page, so bear with me here. Copy, and we'll go to the next page. All right. So here we go. So right now, it's not something I can really graph because, well, first of all, there's no y's. So maybe if this was y is less than or equal to -2x plus 1, that would be the graph of the line. But since there's no y's, I'm going to get x by itself, and we'll have the graph of a vertical line. So to get x by itself, first of all, I need to get rid of this 1 right here. And if you remember with a compound inequality, we do things the same as just a normal inequality, except every time you change something, you have to change it in every spot, right? So I need to do it to the left and the right as well. So for instance, if I'm going to subtract 1 from the 2x plus 1 part, I need to subtract 1 everywhere. So I'll subtract 1 here, and 1 here. And when I do that, I'll get -4. It's less than or equal to -2x is less than 4. All right, and the next thing I need to do is get rid of this -2 in front of the x. So I'll divide everything by -2. And you may remember, if you divide or multiply by a negative number with inequalities, you have to change the direction of the inequality. So -4 divided by -2, that's 2. I'm going to change the direction of this inequality because I just divided by a negative number. In the middle, I've just got x. And oops, this is supposed to be a 2. There we go. And 4 divided by -2, that is -2. And because, again, I divided by a negative number, I need to change the direction of that inequality as well. All right, so here's what we've got. X is bigger than -2, and x is less than or equal to 2. So I'm going to graph this. This defines two vertical lines. So one of them is x is less than or equal to 2, and the other one is x is greater than -2. So I suppose I need to go a little further this way on my graph. Here's -2, here's 2. And so let's start with the +2 first. So x is less than or equal to +2. Since it's a less than or equal to, I'm going to make this as a solid line. There we go. And then I want x coordinates that are less than that line, so I'm going to shade to the left. All right, and the second inequality says that x is greater than -2. Since it is not a greater than or equals to, just a greater than, I'm going to put a dashed line indicating that I can't be on this line. Points ought to lie outside of that line. And I want x coordinates that are bigger than that line, so I will shade to the right. And the solution to this system is everything in between these two lines, and then including, of course, the non-dotted line. So solutions to compound inequalities will be places that satisfy both inequalities at once, or places where I have shading from both sides at once, right? So I wouldn't have anything over here or anything over here because they don't satisfy both inequalities at once. Okay, hopefully that's a good quick review of graphing these inequalities. You can do this on your calculator, but I would not suggest it because, especially when you get a larger system of inequalities, because the shading tends to obscure the graph to the point that you can't even read it. So often it's easier to just graph them on your calculator with an equal sign, and then do the shading yourself on a paper or something like that afterwards. Okay, so that's just a brief review of graphing these things. And then let's go ahead and do some linear programming. And I'm not really sure why they're calling this linear programming. We're not really doing any programming per se, but what we are trying to do is to maximize or minimize a quantity based on a system of linear inequalities. So that's what's going on. So we're trying to maximize or minimize an objective function is what I'm going to call this. Based on a system of constraints. So the constraints are going to be a system of linear inequalities, and then the objective function will just be some function that I can plug x and y into and get a value out the other end. So the best way to show this is just with an example. So the first thing I'll do is put down the objective function. So our objective is going to be to maximize this function. So I've got some function, which I'll call the output of that function z, but it could be any variable you want. And on this one in particular, it'll be 10x plus 10y. Right, so I can plug in x and y, and then I'll get a value for z. Right, so this is the objective. And then I'm going to give myself a system of constraints. So I can plug in any x and y I want to, as long as they satisfy the following system. So firstly, 5x plus 6y is greater than or equal to 95. 15x, let's see, minus 9y is greater than or equal to 150. X plus y is less than or equal to 42. And then x and y are both greater than or equal to 0. Oh, that was terrible. Do that again. Slightly better. Okay. So generally this last line is a little bit weird because I have a comma in there. All that means is it's kind of two equations in one. So x is bigger than or equal to 0 and y is bigger than or equal to 0. And this constraint shows up in probably almost all the problems we do. It just means that x and y can't be negative, right? So if we're talking about a problem that models something in the physical world, often that would be like distance and weight or something like that, right? And those values can't be negative. So this constraint shows up a lot. Okay, so how are we going to solve this? The first thing to do is to graph all of these inequalities. And all of them right now are not in a nice form to graph. So what I would do first is to put all of these in slope-intercept form. So that we can graph them easily. Okay, so let's do that. The first equation, let's see. So I could subtract 5x to the other side and then divide everything by 6. So I would have y is greater than or equal to 95 over 6 minus 5 over 6x. So I've subtracted 5x to the other side, and then I just divided the other side by 6. Okay, second equation. Let's see, I could subtract 15x to the other side and then divide everything by -9. And I would get that y is, be careful here, if I'm dividing everything by -9, I'm going to have to switch my inequality direction. So y is less than or equal to 150 over -9 minus 15 over -9x. All right, third equation, this one's easy. I'll just subtract x to the other side. So y is less than or equal to 42 minus x. And then the last one is already good enough, right? So we know how to graph both x and y greater than or equal to 0. Okay, so those are my equations. And the next thing to do would be to graph this on your calculator. Of course, I don't have a calculator with me now. So instead, I'm going to graph these on Desmos. So if you bear with me just a second, I'm going to stop sharing this and start sharing the Chrome here. Oh, here we go. Hang on. Actually, I have to have Chrome pulled up in order to share it, I suppose. Okay, so there's Chrome. And I'm just going to pull up Desmos graphing calculator. Okay, so I'm going to put these equations into the graphing calculator. And so if I were doing this on my TI-84, I would do all equal signs, right? There's no reason to mess this all up trying to use inequalities because you won't be able to read the end result very well. You can certainly try it, but I just haven't had good luck with getting a good result out the other end. Okay, so there's one equation. Y is equal to 150 divided by -9. Let's see, minus 15 over -9. Okay, so there's another equation. Oh, whoops. I forgot the x here. That's not good. That's an x. There we go. And then 42 minus x. And then lastly, x and y are greater than 0. I think actually Desmos will do the x greater than 0. Yeah, so you can see a vertical line there at 0, and then y equals 0 is a horizontal line. Okay. So of course we got to clean up the window a little bit because we can't see everything. Let's see, is there a good way to do this? That looks terrible. Maybe I can just, yeah, that's better. Okay, so we can see all of the lines now. And now we need to think about the inequality part. So the first equation here, if you recall, this was a greater than or equal to. So I can show you what that would look like in Desmos. Right, so we would need to shade above that line because we're looking for values that are equal to the line or bigger than it. So the line is solid, and then we would shade above. And then if I look at the second inequality here, maybe it'll look good enough on Desmos. Let's try it here. This one was less than or equal to. So we would shade below that line, right? And we're also keeping it solid because points can lie on that line. The third inequality was a less than or equal to. All right, again, line is solid because it's an equal to one, and then we're shading below the line because we want y values less than that. And then the other ones I'll just leave how they are, but we just need to remember we want our y and x values to be positive. Okay, and so that leaves us with only one region where all three inequalities are satisfied at once, and that's this middle little trapezoid region right here. Right, so this is a place where we are bigger than the red line, right? It is a place where we are smaller than the blue line. That's this guy right here. We are smaller than the purple line. Where's the purple? Oh, I guess this is blue. This one's purple, right? But smaller than both of these. And then we are above the x and y axis. So we're in this trapezoid right here. This trapezoid is called the feasible region. Feasible region because it satisfies all our inequalities at once. So any x and y pair that we plug into our objective function has to come from this region, right? I can't plug any x and y from anywhere else because they wouldn't satisfy all of these inequalities. Okay, so, right, so we're gonna need to note where are the corner points of this region. That'll be important here in just a minute. So I guess I'll need to switch back over to my notebook to do that. So sorry, but let me do that real quick. I'll write them down. So if you're following along, we can kind of do this together. Let's see, how do I stop? Okay. And then share notebook. There we go. All right. So what do we got here? So the corners of our trapezoid, starting from the left corner, there's one at 13.5. The top corner is 22.20. There's a corner at the right here, 42.0. And then lastly, there's a corner at the bottom left, 19, 0. Okay, so those are the corners of my trapezoid. And the reason that I wrote down the corners of the feasible region is because of this theorem. So basically, the theorem says that if you're trying to maximize an objective function, constrained by these systems of inequalities, then the objective function, if it has a maximum or a minimum, that maximum or minimum will occur at a corner point of the feasible region. So if there exists, that's not how you spell exists. If there exists a max or min of the objective function in the feasible region, so if one of those exists, it will occur at a corner point. Okay, to find these corner points, by the way, you can do it one of several ways, and hopefully you've seen that in the video on the subject. But the sort of naive way would be to solve a system of equations at each corner. So a corner point is where two lines intersect. So you could always just solve a 2x2 system to find the corner points. The easier way, though, is to go on your calculator where you've already graphed the lines, and then use the intersect feature on your calculator. So there's a little calculate button up with the graphing stuff. And I think there's an intersect feature in there if you click on that. I think the video will explain it better than me without a calculator today, but I'll also do it maybe later on a different day. Okay, but there's an easy way to get these corner points. And once you have them, all you need to do is to determine which of these coordinate pairs makes Z as big as it possibly can be, right? So if I go back, our objective was to maximize this function, Z equals 10x plus 10y. So I'll write that on the next page. So I'm just going to check each of these points because I know if the maximum exists, it has to be at one of these points. So I just have to check here. So let's see. If I check the first point, well, I won't write Z. So the first point will be 10 times my X value, which is 13, plus 10 times the Y value, which is 5. That gives me 130 plus 50, that's 180. So my second point, I'll have 10 times 22 plus 10 times 20. So that's 220 plus 200, 420. So that one's much better. Last point here, let's see, 10 times 42, 10 times 0. Well, that's also 420. Okay, interesting. And then lastly, I've got 10 times 19 and 10 times 0. That's 190. Okay, so is there a maximum? Well, yes, there's two of them, right? So nothing said that we couldn't get two maximum values. And sure enough, we do have two here. So the objective function is maximized for two coordinate pairs. That was 22, 20, and 42, 0. So both of these coordinate pairs would work. And sometimes in a practical problem, you would have to choose, which one of these do we want to use? Sometimes one of them that has 0 as one of the entries is sort of a nonsense answer as well, right? If so, maybe this is a manufacturing plant trying to sell two different things, and they wouldn't want to sell just 0 of one thing, maybe, you know. So you might have to look at this practically to choose which one of these would work. But the mathematical solution, both of these coordinate pairs, maximizes the objective function, right? It gives us the biggest value. So if our objective were to minimize the objective function, we would have chosen the coordinate pair 13, 5, because that gives us the smallest value of the objective function, right? So maximize, look for the biggest value, minimize, look for the smallest value. All right, so hopefully that's not too bad. One point I wanted to make was in this case, in the example we just did, the feasible region was bounded, right? It just looked like a trapezoid, but the region is not always bounded. Here, so oh, there we go. Why is this doing that? Okay, so in this case, that's not how you spell region. In this case, the feasible region was bounded, and this implies both a max and a min must exist, right? And we found the max and the min just now. If the feasible region is unbounded, that is not the case. So an unbounded feasible region, a max or a min might not exist. Maybe only one of them exists, right? You'll have to look at this more analytically. I can give you a short example here. So first, let me write down our objective. So let's try to find both the max and min of this. Right, so of 2x plus y. And then our objective function is going to be constrained with the following inequalities. So y is bigger than or equal to negative x plus 1. Y is bigger than or equal to negative 2x plus 3. Y is bigger than or equal to negative a half x. And then the usual x and y are both bigger than or equal to 0. Okay, and I'll just graph these very quickly. Okay, so negative x plus 1, it's got a y-intercept of 1 and a negative slope. So it will look something like this. Negative 2x plus 3 has a y-intercept of 3 and a slope of negative 2. So it does something like this. Negative 1/2 x has a y-intercept of 0 and a slope of negative 1/2. So it should do this sort of thing. And then x and y bigger than or equal to 0 just means that our points have to be positive. Okay, so if we look at the direction of all these inequalities, we're looking for y values that are above every single line. So that's going to be all this stuff out here, right? Also, my points have to be positive, so things will kind of stop at the x and y axes here because x and y must be greater than or equal to 0. But basically, this is the feasible region, right? So everything above these lines is a feasible region. And you should intuitively see that this is unbounded. It's unbounded because there's no sort of upper limit on what is in the feasible region, right? I can go as far up and to the right as I want to go, and I'm never going to run out of feasible region. What that does mean is that we're not guaranteed to find a max or a min for z. One or both might exist, or none might exist. So let's think about it and see what we come up with. Right, so our corner point theorem says that if a max or a min does exist, that it must exist at the corner points of this feasible region. There's two of them. This guy right here is a corner point. So let's see, what would that be? I think it's 2, 0. And then this guy right here is a corner point, and that's at 1, 2, 3, that's at 0, 3. So those are my corner points, which I can plug into Z. Right, so I can check 2, 0. That gives me 4. And then I can check 0, 3. Oops. And that gives me 3. So if a max or min exists, it will occur here. I do have a bigger point and a smaller point. However, technically I can plug in any X and Y pair in my feasible region to find a Z value. So let's see if I can find an X and Y pair that gives me something bigger than 4. And then let's see if we can find anything less than 3. So something in my feasible region that I think will give me something bigger than 4. Let's try plugging in the coordinate pair 3, 4. That is in my feasible region. I can show you, let's see, 1, 2, 3 over, and then up 4. I believe that's right here. All right, so that's the point we're talking about. And if I plug that in, I will have 2 times 3 plus 4 certainly is bigger than the other point. And I could have chosen a much larger coordinate pair than that, right? Because I can go as far up as I want, and I can go as far to the right as I want. In fact, you can see as x goes to infinity, as we go to the right as far as we can, z will actually go to infinity as well. Right? If you increase x, z will increase without bound. And as y goes as far up as you want, z will also increase. Right, so there's no maximum value. No maximum value in this feasible region. Now, a minimum value looks like it might exist because I am sort of constrained about how far down I can go and how far to the left I can go. So we would assume that 3 is the minimum value, and that is true if you were to try to check other points, right? If a max or a min does exist, it has to be one of the corner points. This is the smallest one, so it's got to be this one. We know a minimum exists because we are constrained in sort of the downward direction. So you could say that we are bounded below in this case. So a minimum does exist. And then since it does exist, the theorem says that it has to be this one right here. So the coordinate pair 0, 3 gives us the minimum. Okay, so if the feasible region is unbounded, you'll want to look at this a little bit analytically and decide, do you think a max exists? Do you think a minimum exists? If one of them does exist, then it has to be at a corner point, and you can check which one will work. But then, you might not have a maximum or a minimum or both. Just something to think about. All right. Let me continue on here. Okay, so here's one more example of what could go wrong. So let's keep do I have the same? Oh no, okay, here's a new objective function. And then our constraints. Okay, just doing a short example here. So our objective function is x minus y, and we're going to try to maximize or minimize this one if we can. And let's see, here's my graph. So 1/2 x plus 3 should look something like this. This is a strict inequality, right? It's not a greater than or equal to, it's just greater than. So I'm going to make this a dashed line. Let's see, 1/2 x plus 1 would be something like this. This one is a greater than or equal to, so this one will be a straight, or I'm sorry, a filled in line. And then we have our normal, the points must be positive. In fact, let's take this last one out. So points can be negative, let's say. So we only have to satisfy the first two inequalities. So if I shade these in, the first inequality says I'm looking for y values above the dotted line. So that's this way. The second inequality says that I'm looking for y values below the shaded in line. And now my feasible region is nothing, right? So the feasible region is where we satisfy both inequalities at once. And that does not happen here. So any x and y value that I pick either satisfies neither inequality, so something like in the middle here. It satisfies the top inequality, or it satisfies the bottom inequality, but there's no way I can satisfy both of these inequalities at once. So there's no feasible region, which means there's no min or max, right? Because I can't find any x and y coordinates to actually choose or pick. So there's no min or max in this example. Okay, so that finishes up sections 3.1 and 3.2. We've also looked a little bit more at section 1.3. If you guys have any questions over the material or anything you want to ask, feel free to email me. We can meet over Zoom, whatever you guys want. Hopefully we'll be back in class on Thursday, and I will see you guys then. Other than that, stay warm, stay safe, and hope you have a good rest of your day.